On quiz 5, we're looking at a partial derivatives question. And I want to talk about why I picked this particular partial derivatives question. So one of the big challenges when we're looking at a function and trying to take the derivative or integrate it or do something to it is to read what's going on in the function. In fact, most of the time when we're learning math, we're just learning what all these crazy symbols mean that we put together. And then we have to learn how to operate with those crazy symbols. So here's a set of crazy symbols. Not that crazy, it's all letters. But here's a set of symbols, and here's the way we want to look at things. Our challenge is to read what's going on in the function and how we could break it apart to decide how to apply the rules that we know. So here's one of the things that we notice. We see two factors. So we see two factors, the x squared and the natural log of x squared y. But the x squared factor is only involves x squared, which only has x. And the natural log of x squared y, which involves x and y. So that's the first thing that we notice. That's the first thing that we want to notice going on in this problem. I see the x squared times the natural log of x squared y. So I see the overall structure of this function is a multiplication between these two factors. The overall structure is multiplication, and so that tells me product rule is going to be a thing. So the overall structure is multiplication. So that's what I would want to notice in this problem. The overall structure is some kind of multiplication. These two factors stick out. Now, the multiplication, we have to concern ourselves with what kind of multiplication we're dealing with. Are we talking about, because we're dealing with partial derivatives? In Calc 1, I could easily just take out this y, we see the overall structure is multiplication, and we use the product rule. But with partial derivatives, we have to distinguish between what kinds of multiplication we're dealing with. In terms of x, for the partial derivative with respect to x, these factors both involve x, so we use the product rule. But in the partial derivative with respect to y, x squared is constant, so we have scalar multiplication for fy. So once we just see the overall structure is multiplication, we have to decide what kind of multiplication in each derivative. So we should be thinking, but what kind of multiplication are we dealing with? Are we multiplying functions or constants? Constant multiple? Or multiplying variables? Not multiplying. I won't write multiplying. Multiplying variables. So even though x squared says this is a variable, when we're taking the partial with respect to y, we're holding x to be constant. So for fy at xy, the x squared is constant. So our multiplication is a constant multiple. But for fx, x squared is a variable, and natural log of x squared y is variable. So now we're using the product rule. So it's constant multiple for xy. Sorry, fy. I spelled y wrong. For fy, x squared is constant. So no product rule. But for fx, we have two functions of x, we have to use the product rule. So for fx, both factors are functions of x, so we do need to use the product rule. Any questions? So that would be how I approach the problem. That would be what I look for when I'm going to think about applying derivative rules. Look for the overall structure. If the overall structure is multiplication, we have to think about what kind of multiplication are we dealing with. Are we multiplying by a constant, in which case we don't need the product rule? Or are we multiplying variable factors, in which case we do need the product rule? Note that we can use the product rule when we're multiplying by a constant, but the derivative of a constant is 0. So that's why we skip the product rule. It takes out one of those terms for us. Any questions? Note that this is on top of the other things that we can do. This problem in particular has a natural log. So maybe there's some fishy stuff going on with the natural log. So this one has this function has logarithms. So maybe properties of logarithms should be something we think about. Not necessarily initially, because we have a technique to apply and it's not going to be that bad to apply. But if we're curious, there might be some properties of logarithms that we can apply here. In particular, we're looking at the natural log of x squared y. And I don't know if this is going to help, but let's just look at this factor, the natural log of x squared y. We can write this as the natural log of x squared plus the natural log of y. And we can write this as 2 times the natural log of x plus the natural log of y. So one of the things that this does for us, first of all, is kind of takes out any chain rule that we might have. And it also breaks things into terms. So maybe that's helpful. So if we have x squared times natural log of x squared y, we can write this as x squared times 2 natural logs of x plus the natural log of y. We'd have to use the product rule here. Maybe we want to distribute them. Oops. It's 2x squared natural log of x plus x squared times the natural log of y. Now we can really see some stuff for fy, here's a bunch of stuff that's going to just drop out because there's no y over here. We only care about this. So using properties of logarithms, we can like kind of preempt the chain using the chain rule. Maybe this helps, but maybe the problem was easy enough before we do some algebraic sleight of hand. And it might just be that I did the algebraic sleight of hand here because I also teach algebra on a regular basis, and so I think about these things. But one of the strategies that we have when we're dealing with integration and differentiation is to try to break things into terms. But the point is to consider all of our options and not just pick one thing and say, this is the way. Any questions? So that's what I would think about for quiz 5. I would actually take the derivative of the two partial derivatives of this. They'll probably be in a different form than if you had not messed with the function before taking derivatives, but they should be algebraically equivalent to each other. So take your answer from this first go through and apply the properties of logarithms to see if they come out to the answers that you get where you take derivatives after applying properties of logarithms. Any questions? Note that I separated out this part here. So that's where we use just use the properties of logarithms. And then I put it back together into the original function. Any questions? Does that help clarify quiz 5 a little bit? Right, let's pause the video here. Talk about some more problems.